A high-speed digital sensor firing millions of data points a second collides with a microcontroller that reads data at a fraction of that speed. Because these two hardware components are driven by completely independent clock frequencies, they are asynchronous. They do not share a common heartbeat. If you attempt to wire that high-speed data stream directly into the slower domain, you get physical collisions. Signals arrive while the receiver is looking away, causing dropped bits, corrupted data, and complete system failure. To bridge that gap, hardware engineers use a specific architectural component, the asynchronous first-in, first-out buffer, or async FIFO. It acts as an elastic shock absorber. It takes in data at the transmitter's blistering pace, stores it safely, and allows the receiver to pull that exact same data out at its own, slower rhythm. At its core, a FIFO is a dual-port memory array. Data enters on the left, exiting on the right. A write pointer tracks exactly where incoming blocks are written, while a read pointer tracks the oldest data ready for extraction. When the receiving clock pulls that data out, the operation is logically destructive. The read pointer increments forward, leaving the old data behind to eventually be overwritten. To prevent the system from overwriting unread data or reading empty slots, the FIFO continuously compares the exact binary positions of these two pointers to generate empty and full warning flags. Safely managing these pointers is the entire mechanism of flow control. If the logic fails, the buffer overflows and the hardware breaks. Now we split the system clock: write logic on a fast clock line, read logic on a slow clock line. To evaluate if the array is full, the write logic must read the read pointer's position. A signal must cross the asynchronous boundary. Look at this timing waveform of a binary counter. When transitioning from a 3 to a 4, 3 bits must change state. Minute physical differences in copper routing cause tiny misalignments. If the clock strikes during this transition window, it might sample a garbage value. This physical instability is called metastability. The receiving flip-flop catches a voltage right in the middle of a transition, getting stuck in an unpredictable state. When that garbage pointer value hits the comparison logic, the FIFO registers a false flag. The transmitter stalls, or valid data is permanently overwritten. Standard binary counters are mathematically incompatible here. To safely transfer data across an asynchronous boundary, the sender must follow one strict rule: change no more than 1 bit at a time. This table compares a 3-bit binary count sequence next to a 3-bit gray code sequence. Look at the binary side transitioning from 3 to 4. 3 bits flip simultaneously. Now look at the corresponding gray code transition. Only a single bit changes state. This single bit change solves the sampling error. If the receiving clock strikes exactly on the transition, it samples either the valid old value or the new value. There are no intermediate states. Gray code acts as a mathematical shield. It transforms the physical uncertainty of clock timing into a secure choice between two valid states. However, even with gray code ensuring only 1 bit changes, that single changing bit can still trigger metastability if sampled precisely when voltage is rising. A metastable flip-flop gets stuck hovering ambiguously between a logical 1 and 0. It radiates an invalid, uncertain voltage level deep into the receiving circuit. To cure this hardware-level instability, Verilog designers implement a specific structural solution, the 2-stage synchronizer. This architecture chains 2 D flip-flops driven by the receiving clock. The first flip-flop takes the raw, metastable hit, acting as a quarantine zone. During the clock cycle it takes to travel to the second stage, that voltage settles into a stable state. By the time the next clock edge arrives, the second flip-flop registers a clean, resolved value, safely locking the pointer into the new clock domain. This hardware synchronization costs a few clock cycles of latency, but guarantees absolute physical reliability. We synthesize these components into the complete asynchronous FIFO architecture, combining the memory, gray converters, synchronizers, and flag logic. Notice the high-speed data payload bypasses the synchronizers entirely, dragging directly into the memory block. The actual data stream is never synchronized. Forcing massive payload through a flip-flop chain destroys throughput. Instead, trace the memory pointers. The write pointer converts to gray code, moves through the synchronizer block, and arrives at the flag comparator logic. Keeping the data path raw allows maximum transfer speed. Only the much smaller, low-speed control pointers pay the latency tax of synchronization. True architectural efficiency requires intelligently isolating and safely synchronizing only the critical control states, leaving the payload untouched. When writing basic Verilog, a single clock always block seems sufficient, but for real-world system-on-chip designs, that approach fails entirely. The gray code plus synchronizer pattern is a universal standard in professional ASIC and FPGA engineering, used whenever multiple dense clock domains interface with one another on a single chip. Hardware engineers must explicitly define these physical timing boundaries in their code, so the synthesis tools know exactly where the asynchronous handoffs occur, ensuring the synchronizers aren't optimized away. Logical correctness in Verilog only works if the rigorous physical timing constraints of the underlying silicon die are perfectly respected. Mastering the internal architecture of the asynchronous FIFO demonstrates the ultimate transition from merely writing code to engineering robust physical hardware.